All right. Hello, everyone. Now we are talking about the part 1 of lecture 3, and we're going to give a quick review over the concept of predicates and implications. Okay, so there are a few concepts surrounding predicates involving what's a predicate, what is a quantifier, how to negate a quantified predicate. So a predicate P of x is a statement that incorporates one or more variable x such that whenever x is specified, px becomes either true or false, okay? So in other words, when we replace the variable in the predicate with values, we have a proposition. And we're going to give a few examples very soon. And then the domain of a predicate is a set of variable values for which the predicate can be evaluated. Okay, all of this sounds a little bit abstract, so let's look at a few examples. Okay, so the predicate P of n means that it's a statement that n is even. So in other way of thinking about integer n to be even is that when I take the quotient, that the quotient, if I take quotient with 2, it has 0 remainder. Okay, so another way to think about it is that, you know, if it's an odd number, if I take quotient over 2, it has a remainder of 1. Okay, so what is the domain of this predicate? The domain is treating integer, and in our situation, integer has a symbol of z. Okay, and now we can evaluate for the variable n if variable n is taking various values. For example, if I evaluate this predicate when n is equal to 1, 1 is not even, so the evaluated result means that it's false. If I evaluate this predicate, you know, is 4 even, then it's true because 4 is indeed even. Similarly, if I evaluate over n equal to 5, it's false. N equal to 105, it's false. If n equal to 2000, it's true because if I take a quotient, if I take the remainder of dividing by 2, there's nothing remains, okay? Now the second predicate here is the predicate if x is bigger than 15. So in this case, we're going to say that the domain is all the real numbers, and we can evaluate this over 3 numbers, for example. For the first thing is when the number is equal to 3.1, 3.14, which is approximation of the number pi. Is this bigger than 15? No. So this is evaluated to be false. Is 15 bigger than 15? No. So this is evaluated to be false. And is 15.6 bigger than 15? Yes. So this is evaluated to be true. The next one is a more complicated proposition as part of the predicate. The predicate, which takes the input as y, is asking is y bigger than 5 and is y smaller than 20. Again, we are going to give ahead of time that the domain of this is integer, and we can now evaluate for a few integers. For example, if I evaluate over 1, 1 is definitely not bigger than 5, so it's already evaluated to be false. If I evaluate 10, is 10 bigger than 5? Yes. And is 10 less than 20? Yes. So this whole thing evaluated to be true. And now the next one is 100 bigger than 5? Yes. If 100 less than 20? No. So this evaluated to be false. So those are some examples of a predicate. And now you might have guessed, if I have a predicate that some of those input variables has evaluated to be true and some of them evaluate to be false. So you can think about the predicate as it actually partitioned the domain into 2 parts. All the values which evaluate to be true and all the values evaluate to be false, okay? So The question is, does a predicate become true for elements in the domain? Some predicate will never be true. Some predicate is always true, and some predicate is occasionally true, or sometimes it's true, sometimes it's false. Okay? So now let's look at predicates and negations. So if I look at the set of values for which a predicate is true, then that defines a subset of the domain. Sometimes maybe the entire domain, this is true, or sometimes it's only a subset, well, a proper subset, meaning that it's not the entire domain, but it's only a subset. And sometimes maybe nothing in the domain, this predicate will evaluate to be true. So, you know, the part of the domain that the predicate is true is now empty set. Okay? So we can always write the negation of a predicate as another predicate that specify the complement of the set. So again, you know, if I have a predicate that always evaluate to be true for everything in the domain, if I take the negation, then nothing in the domain will evaluate to be true. Again, this is better understood through some examples. We're going to see examples in the part 2 of this lecture. Right now, I'm just giving a high-level overview of some of those concepts you have already read in the textbook. Okay, so there's a few important symbols for putting in front of the predicates. So the first one is this symbol, which means it's an element. Okay, if I say K belongs to D, you know, using this symbol, it means K is an element of D. The other symbol you're going to see a lot is for all. Okay, this means that, for example, if I have this thing here, it says for all element S in the set. If S represents, say, all the students, and then C means the class, then it says for all the students in this class. The next symbol is exists. So for example, if I have exists I in lowercase I in capital I, it means there is some element that is in the larger set I. But the whole statement, again, if S means a student, C means the class, then the statement says for all students in this class, there exists a number I, which is a valid student ID. Okay, so, you know, of course, you know, I'm putting a lot of assumption here, knowing what I stand for. In this case, lowercase I stand for a particular ID, and the capital I stand for the set of student ID. We're going to learn the concept of set in the chapter 3, but you're going to see some of those examples already. For example, we are already talking about the set of integers and the set of real numbers. All right. Okay, now let's talk about quantifiers, right? So the symbol exist and then symbol for all are called quantifiers. So when you combine a quantifier with a predicate, the resulting statement is known as a quantified predicate. And a quantified predicate is true or false, of course. So now let's look at some examples. Oh, and also last thing we want to do is negation. So if I have a quantified predicate, I can put a negation in front of it. So which is basically the operation called negating the quantified predicates. So what does this mean? The typical rule is the following. If I have some statement involving for all variable x, if I take the negation outside, this is equivalent in flipping for all into exist sign. That's the first thing. For example, if my statement is for all x in the domain, I have some predicate. If I put negation on the outside and I want to bring it in, then what's going to happen is this for all symbol is now switched to exist symbol, and the statement P of x is now its negation. So another way to think about negating a quantified predicate is to bring the negation symbol inside the parentheses and do it step by step from left to right. Again, this will become clear when we start doing some practice problems. Okay. Another thing to think about negation, again, if I negate something involving existence symbol. So if I negate where inside the statement there is existence, then I'm flipping existence back to for all. Okay. So again, if you think about from English perspective, the opposite of exist at least one element to be true is to say that for all of the element it's false or there does not exist. Okay. So again, if I'm thinking about this, if I have a statement in here that involving existence and involving a predicate, if I bring the negation inside, this existence symbol now flip to for or symbol, and correspondingly, my predicate is become its own negation. So again, the process is moving from left to right. And if you see an existence, you flip to the for or symbol. If you see for or symbol, you flip it to existence symbol. And if you see a predicate, you flip to the negation of that predicate. Okay, so let's do this, okay? So of course, there's a step-by-step way of doing this. So let's do this example slowly, okay? So remember the rule is I'm going to process from left to right, one term at a time. And when I see existence, I translate to for all. When I see for all, I translate to existence. So now the first step, okay, is I'm bringing this negation inside the first term. So because I see a for all term, this became existence term. So now I have flipped the first symbol here. But now I'm going to do it gradually, so I have not dealt with the rest of it. Okay, now I'm going to try to bring negation into the second term. So if I focus on the second term, there is an existence symbol. So I'm going to flip it back to for all. And I'm going to not deal with the third term yet. Okay? Now I'm going to deal with the third term. Now this is a predicate, which is x plus 2y equal to 3. The negation of it is x plus 2y is not equal to 3. Now we are done. Okay, it's a step-by-step process and from left to right. Okay. And then of course, the place we're going to pay attention is when you see existence, you flip back to for or. And if you see this negation, you're obtaining the corresponding negation term. I should actually use this yellow. Let's use yellow here. Okay. All right, let's look at the next. Well, this is just the whole process, just repeat again in a better typed font. Now we're going to talk about implications. There is what's an implication, what is a negation of implication, what is a corresponding converse, inverse, and contrapositive. And finally, we're going to talk about what is a biconditional. Okay. So an implication is a statement of the form, if P is true, then Q is true. And then the shorthand statement is P implies Q. So when P is true, it implies Q is true. And P and Q are basically different propositions. And sometimes P is referred to as hypothesis and Q is referred to as conclusion. Okay? And English shorthand is if P, then Q. And then the logic shorthand is what I just write down here, which is P, right arrow Q. Right? So if P, then Q. So it also have a lower precedence than any other logic operations. For example, if I have something like, A or B implies C and D, in this case, this implication symbol is evaluated last. Okay. So of course, there is the corresponding truth table associated with implication. Again, the first two columns are all the possible combinations of truth values for P and Q. And what's interesting is if P is true, Q is true, then P implies Q, the implication is true. So that's the first row. The most important part is actually the second row, is that in the truth table for implication, if P is true, Q is false, then this implication result is false, okay? Again, the other thing you want to remember, if P is false, Q is true, then the implication is true. And when this is also something to pay attention to, if P is false, Q is false, then the implication is true, okay? So later on, you're going to start seeing some proofs involving implications. In order to prove an implication, you need to show that this will never happen. To disprove the implication, and you want to show that this can happen. In other words, you want to find a counterexample. Again, this will become clearer later when you actually study proofs. Okay? But the very important part is to understand the colored part. If both P and Q is false, the implication is actually true. Okay, now we have the next thing, which is what's the negation of implication. So what is a negation? If I negate the implication where P implies Q, it's logically equivalent to P and not Q. Okay. So it's actually quite important to notice if I take the negation of implication, the result is no longer an implication. The result is actually a form of and statement, right? It's P and not Q. But of course, we have the following question. Why are those two things logically equivalent? The way to prove it is to derive the truth table and then make sure that the corresponding column are actually identical. For example, what you want to show is after you fill the truth table, this column right here and this column right here have exactly same corresponding truth value, which in this case is true. So I would challenge you to try to cover this, only focusing on, try to fill, if I'm only giving you the first two columns, and the label of the first row, try to fill this truth table on your own to convince yourself that those two things are actually logically equivalent. Okay? Now, we just learned the negation of implication. So let's put it right here. If I have negation of P implies Q, it's logically equivalent to P and not Q, right? So again, this is a quantified implication and you are taking a negation in front of it. So what do we do? So how can we negate this statement, right? There's a quantifier at the very beginning. So now if I negate this thing here, again, the process is bring the negation symbol in. The moment you do that, you're going to flip the sign of for or back to existence. So this become exist X in D, and then you want to negate the implication. Okay, if I want to negate the implication, what I get as what I showed here on the left-hand side is negate of P implies Q is P and not Q. So this is Px and not Q of X. So that's it. Again, I have typed the result here, so it's easy for you to review it later. Again, I'm going through the example a little bit, in sort of a speed where when I say, try this problem, you could pause the video and try to solve this on your own. And then you can match your solution with the solution provided. So there is a few more concepts. If we are giving an implication, P implies Q, then there is the concept of converse, which is Q implies P. There is a concept of inverse, which is not P implies not Q. And then there is a concept of contrapositive, which is not Q implies not P. Okay, so if you're thinking about deriving some form of cheat sheet for your quiz, this might be something you want to put in on cheat sheet, because there's a minor differences between those definitions. If you're not careful, you might be using the wrong one. Okay, so if we want to kind of simplify those concepts a little bit, one thing that is known as important properties involving those concepts is, first of all, an implication at its contrapositive or logically equivalent. So what is my implication? P implies Q is my implication. What is a contrapositive? It's not Q implies not P. And my statement is that those two things are actually logically equivalent. How do you prove it? By truth table. Okay? The second thing is to say, okay, the converse and the inverse of the implication are again logically equivalent. Okay, what is converse? A converse of implication of P implies Q is Q implies P. This is a converse. What is the inverse? The inverse is not P implies not Q. So again, those two things are equivalent. In fact, they're equivalent because the thing on the right-hand side is actually the contrapositive of the thing on the left-hand side. Okay, so hopefully this will convince you. Again, this is just applying the equivalence of contrapositive with the implication itself. It's just you're doing this between converse and inverse. Now, the last part is actually really important. An implication P implies Q is not logically equivalent to its inverse. What is in inverse? Is not P implies not Q. Again, if you do a truth table, you will be able to see why those two things are not logically equivalent. Okay? So the last concept we have is called biconditional, right? There's a word bi in it. It means there's two directions it's going. So if I have this double arrow here, it means P implies Q and Q implies P. Another way to write it is to say P double arrow Q is logically equivalent to say P implies Q and Q implies P. Sometimes in English, it means P is true if and only if Q is true. Or in shorthand, you're going to see this symbol. Okay? So for example, I can have the following statement: x squared is even if and only if x is even. X squared is odd if and only if x is odd. So I would like you to think about this at take home to prove why those two things are actually a true statement. Okay? If a number is even, then the square is even. If the square of the number is even, then the number is even. And later on, you're going to see this kind of proof for chapters in chapter 3. Okay, so of course, I just said that those two things are logically equivalent. Okay, to prove it, you can use a truth table. Okay, so again, it would be interesting for you to look at the truth table to see how does the corresponding things are. For example, again, if you focus on biconditionals, if you have all possible combinations, you get the last one, meaning that if both P and Q is true, then the biconditional is true. If P is true, Q is false, then the biconditional is false. And again, and so on and so forth. Okay, it's again important to notice the last row of this. What does this mean? Oh, let me just do a little bit slightly better. What does this mean? It means if P is false, Q is false, the biconditional is actually true. Okay, so this is a little bit counterintuitive, but that is the property associated with the biconditional. The last one is, can we write P if and only if Q without using the arrows? Okay, so I put the answers here, and then this is where you can pause it and try to think about how can I do this problem. Here is a potential way. Remember I said earlier that the biconditional can be written as unidirectional, but having two parts. So P if and only if Q is logically equivalent of P implies Q and Q implies P. And there's one more property that we have not used before, which is P implies Q is actually logically equivalent to not P or Q. Okay? So again, it would be an interesting take-home practice to try to prove to yourself left-hand side and right-hand side of this property is actually logically equivalent. Again, you can use a truth table. But if I do this, then I can replace the first term by not P or Q. In the second term, I apply the same rule I wrote on the upper right-hand corner. I can write Q implies P is not Q or P. Okay, and that's exactly the solution I typed at the bottom. Okay, so that's it for the first part. I'm reviewing certain concepts affiliated with implication and quantifiers, and in the next part, we're going to do a lot of practice problems.